Welcome back. This is an Aleks training video on using reactant reaction order to predict changes in initial rate. A rate law tells you how fast something is happening based on the concentration of the reactants. Okay, so if I change the concentration of reactants, the rate law will tell me what it does to the rate of the reaction. So how fast the reaction happens. So if I double the concentration and it's in first order, then it's to the 1 power, then it's just doubled. If it's to the second power, then I double it twice. I have to double it and then double it again since it's to the second power. So the rate law gives me information of what the rate is based upon the concentration. So this tells me that a certain reaction is second order in nitrogen and first order in hydrogen. So this is what it looks like. You're always going to have a constant, a rate constant. It's a number that makes all the math work. So your rate is some number that you could figure out times the square of the concentration of nitrogen times the concentration of hydrogen. Okay, so they're going to give you some information and you could figure out K. You may need it. We're going to need it for one of these problems, I think. You don't need it for everything, but if you could do it, go ahead and figure it out. It's going to give you the initial rate, so that's rate. It's going to give you the initial concentration of the nitrogen and the hydrogen. So let's figure this out. If they tell you that the initial rate of reaction is 1 times 10 to the 6th molar per second, and they give you everything but K, I guess we could solve for K. K is going to be equal to the concentration of nitrogen twice. Okay, so that's 2.39 squared. See, I've moved it from the right down to the bottom. And then the concentration of hydrogen to the 1 power. So 1 times 10 to the 6 divided by 2.39 equals divided by 2.39 equals divided by 1.71 equals 1.0237841 times 10 to the 5th. Okay, so that's K. And if you need K, you can figure it out. If you don't need K, don't use it. So at least we have it. So let's see what the first question is. All right, so you're filling in this initial rates. So what's happened to the nitrogen? What's happened to the hydrogen? If something happens to something to the 1 power, all you do is multiply it by that number. So if it goes up by 4.31, then multiply the rate by 4.31. If something is to the 1 power, you don't have to modify it at all. Okay, so in this first example, nitrogen stays the same, the hydrogen goes up. Okay, so how much does it go up? Let's divide it out and see. So I have 7.45 divided by 1.71. It's going to go up by, okay, it'll go up by 4.356725146. Okay, it's going to go up by that much. So since it's to the 1 power, all I have to do is take the initial rate of reaction and multiply that. Okay, the initial rate of reaction was 1 times 10 to the 6. The concentration of H2 went up by 4.3. That means the rate's going to go up by 4.3. Okay, so since it's to the 1 power, okay, whatever you do here, if I double this, I double the rate. If I triple this, I triple the rate. If I go up by 4.356, then I do the rate by the same amount. So I'm going to multiply 4.3567 whatever times 1 times 10 to the 6 and I get this first one as 4.3, let's see, how many significant digits? These are all to 3, so I need to go to 3 significant digits. So it's 4.36 times 10 to the 6th molar per second. Okay, so all I did was go up. If the nitrogen went up, remember you would have to take 4.36 and then square it, and then take that number and multiply by the reaction. Okay, because it's in squared, you'd have to square however much it went up. Since the H2 was just to the first power, whatever it went up, multiply that number. But if it's to the second power, you have to square it first and then multiply it by the amount. Okay. This last one, though, they both went up. And since they both went up, I don't know how to do that other than to simply put them all in and use K. So we're going to use the K. We're going to use the K that we solved before, 1.02. And I'm just going to do the rate. So I'm just going to say rate equals 1.02378, that's probably enough, times the n squared, in this case, is 0.845. And remember, the n squared is to the second power, times the hydrogen, which is to the first power, 4.83. When I do the math, the rate is going to be equal to 3.530763565 times 10 to the 5. All right. I want to do it to 3 significant digits. So it's going to be 3.53 times 10 to the 5. And that's what this is. 3.53 times 10 to the 5th molar per second. Okay. Not hard, I think.